I'm Anil Kumar. Welcome to my series on calculus. We'll discuss a test paper on curve sketching in this particular video. I've taken some questions here from previous test papers. So in the beginning, I'll share with you multiple choice questions and then we'll take a few knowledge and thinking questions. I'd like you to pause the video in between, answer the questions first and then look into my solutions. Question number 1. Let the derivative of the function be x plus 3 times x minus 3 whole square as shown in the graph. For what values of x is f of x decreasing? Now I've drawn a graph here. At times the graph may not be given to you, right? So here we have the graph as well as the equation. We are given graph of the derivative of the function. This is the derivative of the function which is shown on the graph. You have to find for what values of x is the function decreasing, correct? Now when is the function decreasing? Function decreases when the derivative is negative or less than 0. Now from this sketch you can see it is less than 0 on the left side of minus 3, right? This graph is not to the scale. Now since it is to the left side, that is a choice which we are looking for. So for x which is less than minus 3, the function will be decreasing, right? So that is how you are going to answer this question. Don't look into this interval from minus 1 to 3. Here the derivative is decreasing but positive. Do you understand? Derivative is negative only on the left side of minus 3, right? So that is where the function is decreasing, correct? Question number 2. If f of x is increasing for every x greater than 5, then which of the following choices is possible for the derivative, right? So we are saying that f of x is increasing, right? So means f of x is greater than 0 for x greater than 5, right? So increasing really does not mean f of x. F of x is increasing means the derivative is greater than 0 for x greater than 5. Do you understand? So when we say f of x is increasing, that means the derivative is positive, correct? So this is the key to answer. Amongst the given equations, where is the derivative positive? Now here it is negative 5, which is wrong, and this is a parabola with negative, so it will be negative in some interval. Here again, for x greater than 5, right? For x greater than 5, this value is going to be negative, right? However, for x greater than 5, d will be positive. Therefore, that is the answer, because this will lead to the derivative being greater than 0 for x greater than 5. Does it make sense to you? That is how we are selecting option D. So I hope this is absolutely clear. The next question here is question number 3. Let the derivative at c be equal to 0, right? So when the derivative is 0, it's a critical number, so we have used c here. If the derivative of the function exists and is decreasing in the interval containing c, then what type of critical point is located at x equals to c? So I hope you understand the question. You can actually now pause the video, answer the question, correct? So what we are trying to say here is something like this, that at c we have derivative which is 0, right? So let's say we again plot the derivative of the function. Derivative exists and is decreasing and on an interval containing c. So in this interval it is decreasing, kind of like this. So when it is decreasing, you will notice that the derivative is positive on the left side of c and negative here, correct? Now if the derivative is positive, that means what about the function? Function is increasing on this side and then decreasing. So what we have is a local maximum. Is that clear to you? So we get local maximum at this point. So option B is the correct option. So I hope you understand the concept. This is a very critical question which most of the students might not get as correct. Okay, let's move on and take the next question now. Question number 4. Graph of derivative is shown below. So in all these questions, we have given you the graph of the derivative. For what value or values of x does the function has a point of inflection? So we need to find point of inflection, and what are we given? We are given the derivative. Okay, so when do you get point of inflection? So for point of inflection, what is important? The second derivative should be equal to 0. This is first thing. So that is, we are looking at these 2 points, right? So for the derivative, these 2 points are the second derivative. So at these points, we have a possibility of a point of inflection. This is one condition, right? The second condition is that the second derivative should be changing from positive to negative, right? So second thing is at point of inflection, if this is point of inflection, then we should have change of concavity. That is to say that the second derivative f dash x will change from positive to negative or from negative to positive. Is that clear? Now in this case, you can clearly see that at these points here, the second derivative is positive, right? And on this side, it is negative, correct? So definitely we have this as a point of inflection. In this case, it is negative, and on this side, it is positive. So it changes from negative to positive, being 0 at the turning point. So this is also a point of inflection. So we have 2 points of inflections, which is at -2 and 1. So option B is the correct option. Is that clear to you? Now that summarizes in short most of the concepts which you learned about curve sketching and how first and second derivative analysis can help us find maximum minimum point of inflection, the concavities, right? Now here is question number 5 on the similar concept. If the second derivative is greater than 0, what else is true about the graph of f of x? Now when I say second derivative is greater than 0, it means what? It means that the graph is concave up, right? So that is the type of graph, right? So here the second derivative is positive, correct? Now look into this part of the function and then answer. So the first derivative is decreasing. Okay, first derivative is decreasing. Well, here it is minus, here it is 0, right? That is the function, and this is your first derivative. This is your first derivative. Clear? So tangent goes from negative to positive, 0, negative to 0 to positive, right? So it is increasing. So it is not decreasing, it is increasing. So first thing is, since the graph is concave up, we are looking into one of these choices. Is that clear to you? Second, the first derivative we saw is increasing. So it is increasing, right? Increasing first derivative. It goes from negative to 0 to positive, and therefore option C is the right option. Is that clear to you? Correct? So that is how you're going to answer these multiple choice questions. Now here is question number 6, which is determine equation of all asymptotes and behavior around them. So we have a rational function here. Now in this rational function, what do you notice? So one thing is that the degree of numerator is higher, 1 higher, right? Is 1 more than the degree of the denominator. That means what? That means we have an oblique asymptote. Clear? So we have an oblique asymptote. Now let's figure out what this asymptote should be. Best way to find this oblique asymptote is to divide, right? So what we are going to do here is that we are going to divide x cube plus 1, which is, we have a placeholder to place since we have two terms missing here, right? We have to divide this by x squared plus 3x. So first let's multiply by x, you get x cubed plus 3x squared. So when you take away, you get minus 3x squared. So you have to multiply by minus 3 and bring down this 0x, okay. So when you bring minus 3, you get minus 3x squared and you get plus 9x. And when you take this away, you get minus 9x and you bring down 1. Clear? That's what you get as your remainder. So clearly, we have an oblique asymptote which is x minus 3. So let me just sketch this here. So x minus 3 means y intercept is minus 3, slope is 1, so something like this. Is it okay? So this is your oblique asymptote, which is y equals to x minus 3, right? So that is your oblique asymptote. Perfect. So we got one oblique asymptote in this case. Now let's also find the other asymptotes. Then we'll talk about the behavior around them, right? So about the denominator. Now we got one, which is because of the numerator being 1 degree higher. Now let's find the denominator becomes 0 when we have, let's factor this out. So we have x common factor x plus 3. So that means x equals to 0 and x equals to minus 3 will give us vertical asymptotes. Correct? So let me draw the vertical asymptotes. One is at x equals to 0. The other one is at x equals to minus 3. Okay. So we got these, there are three asymptotes here, right? So we have three asymptotes, two vertical asymptotes and one oblique asymptote at y equals to x minus 3. Okay, now we'll talk about the behavior around them. So let's talk about the oblique asymptote itself. The remainder here is negative. Do you see the remainder is negative? So when you when you do multiply by minus 3, you actually get minus 9. Sorry, so this should be positive 9. Correct? So when you take away, you get positive 9. Okay. Sorry for that. Minus 3 times plus 3 is going to be minus 9. So it will be plus 9 here. Okay. Now let's talk about behavior, right? So we'll talk about behavior. So we say when x approaches infinity, right? So large positive value. In that case, remainder is positive, right? So 9x plus 1 is positive. So we say that the function is greater, right? So basically, you could write this function as equal to what? You could write this as x minus 3 plus 9x plus 1 over x squared plus 3x, correct? So when x is large, we are adding something to the line. This is positive, right? We are adding something to the line. So that means you're approaching from top. Do you understand? So when x is greater than infinity, in that case, the function f of x is approaching from above, right? Is actually approaching from above. Is that clear? Because it is more than x minus 3, right? Y equals to x minus 3. But when x is approaching negative infinity on this side, this term becomes negative. The denominator, x square, is dominant, will be positive, correct? But the numerator will become negative, and therefore the whole term becomes negative, and you are decreasing something. So it approaches, the function approaches from below. As indicated here. Is that clear to you? Correct? So that is how you have to decide the behavior near the asymptotes, the oblique asymptote as shown here. Perfect. Now let's talk about the vertical asymptotes, right? So let's look at x equals to minus 3. So that is a vertical asymptote, correct? Now in this vertical asymptote, when x is approaching minus 3 from the left side, which is from the left side, in that case what happens? So in this function, when you make this as negative, then the numerator, which is the cube, or you can use this factor. Let me use this factor that is easier to work with. So let me write down the function separately in the factored form to understand the vertical asymptote. So we'll write f of x as equal to x cubed plus 1 over, we'll factor out. So we get x times x plus 3. Is that clear to you? Right. Now, if I have a number which is more negative, in that case, we have negative on the top, right? X is negative, and this term is also negative. So we have 3 negatives, right? So if you have 3 negatives, that means you're approaching from this side, right? So you are on the vertical asymptote, you are on this side, negative. Do you understand? But when x is approaching minus 3 from the right side, in that case, well, this is negative, the numerator is negative, denominator, this x term is negative, however, this term is positive, correct? So in that case, we are approaching this towards the positive infinity. Does make sense to you? Correct? So that is how we are going to answer this question, right? So it is approaching positive infinity. Now let's look into the asymptote at 0, right? So is that clear? So in that case, y, or we can say f of x, is approaching positive infinity. In this case, f of x is approaching negative infinity as shown here. Now when we are approaching 0 from negative or positive side, then what happens? Let me use another ink here. So when x is approaching 0 from the negative side, so when x is approaching 0 from the left side, the numerator here is positive. In the denominator, we have this as negative. However, this term will be positive. So y value, or f of x, is approaching negative infinity, right? So on this side, it is approaching negative infinity, correct? Now, when x is approaching 0 from the positive side, this side, all these terms are positive. So f of x is approaching positive infinity. Is that clear to you? So that is how we are going to describe the behavior near or around the asymptotes. Is that clear to you? Perfect. Now let's move on and take the next question. Question number 7. Using the graph of f of x, state the point or interval for each of the following. So that is the graph for the function f of x. Derivative is greater than 0. So derivative is greater than 0 means what? The function is increasing, right? That means f of x is increasing. Now with that in mind, I'd like you to write down the interval. The second point is, second derivative is 0. Second derivative is 0 means we have a point of inflection, correct? Right, so in our case, this is the point of inflection which is at -1. So we can write this as x equals to -1, right? So from the graph, you can see wherever the change of concavity is there, the second derivative is going to be 0 in a polynomial shown here, right? Okay. Now, next, f of x is less than 0 and the derivative is equal to 0. Now, derivative equals to 0 means horizontal tangent, right? This means horizontal tangent. So we have two horizontal tangents in this graph. Now we want to figure out when is the function negative. So the function is negative here, correct? So the point is at x equals to 2, right? So we have here x equals to 2. Is that clear to you? Right. Now the first one, f of x is increasing whenever the derivative is greater than 0. So the interval is what? So in the first case, the answer should be, let's write down, from -infinity to -3, right? F of x is increasing, therefore it would be positive. So if I draw a tangent line anywhere, it is increasing, right? The gradient is positive. So one interval is from -infinity to -3, or you can say x less than 3, and the other interval is from 2 to infinity. So the other one is from 2 to infinity, correct? So in these two intervals, what we see is the derivative should be positive. Is that clear to you? Derivative positive means if I draw a tangent, it is rising, correct? So it is positive in these intervals. So from here and here, right? So these two intervals. So I hope this is absolutely clear. There are 10 questions. Here is question number 8. Sketch the graph of the derivative function for the function illustrated below. Use same set of axes. Indicate point of inflection, right? Okay, so we are actually given point of inflections here. So these are the point of inflections. We are given you the graph of function. You need to sketch the graph of the derivative, right? So now let's sketch the graph of the derivative, right? You can pause the video, answer this question, and then look into my suggestions. Now when we are looking at the derivatives, we should begin with horizontal tangent lines. So all these turning points will give you horizontals. So we have a 0 here, 0 there, and a 0 matching. So these are the three zeros for the derivative. Clear? This portion is negative slope, right? So in this portion we have negative, here we have positive, right? Here again, after the turning point, which should be negative, correct? Since if I draw a tangent, it will be negative, 0 here, and thereafter we expect positive. Is that clear to you? So we have a negative portion here, and then positive. Now at the point of inflection, what do we expect? For f dash x, since it is positive, and the, here we expect local, maximum for f dash x, right? So we'll get the maximum rate of change. So here we get local maximum rate of change, correct? So at a point of inflection, note, at point of inflection, what do you expect? You get maximum or you get minimum rate of change. Now this is a very important criteria to understand. Is that okay? So we know it is negative here, 0 there, turning point, correct? And up to this place it is positive, then negative. So based on this, we have a turning point here and we have to go from here. And then the next turning point will be here. Do you understand? So that is the turning point. This is the turning point somewhere. So we can now sketch the the graph, right? Here, this is the turning point. So let's sketch the graph. So we'll go like this, kind of, right? I mean, so it turns again, goes through the zero. Right? Do you see that? Well, it has to be a smooth curve. Correct? So it's like a cubic function. So nicely sketch a cubic function graph for the derivative of this function with zeros as indicated and those matching with the point of inflections, the maximum minimum values. Is that clear to you? Correct? So that is how you're going to sketch the derivative of the function. Question number 9. Apply the algorithm to sketch the graph of the function and describe its characteristics. Now, algorithm may be different for students in different parts of the world. What we normally do is first we try to understand the function and then we find its intercepts and then we find derivative, analyze derivative to find local maximum minimum, and then we do second derivative, find concavities, point of inflection, and then we sketch the graph. Is it clear? So that is the algorithm. So first part is to understand the function itself. So we know f of x is equal to 3x to the power of 5 minus 5x cubed. Now clearly this is a polynomial, right? Degree 5. Leading coefficient positive. All this is given to us, right? So as soon as we get a polynomial, degree 5, leading coefficient positive, we know graph moves from left to right, right? So the graph moves from left to right. It is continuous. Correct? Smooth curve. So from the characteristics, you get so much of information once you know the function, right? So basically, we're trying to say here that the graph actually moves from quadrant 3 to quadrant 1, right? So that is the behavior, right? So that is how the graph is. So here, you could write many characteristics which also include that when x approaches negative infinity, f of x approaches negative infinity, and when x approaches positive infinity, f of x approaches positive infinity. Is that clear to you? Now this is a very important characteristic which should be mentioned. Next step, we could actually factor this, right? So we could write the function f of x as equal to factoring x squared will give us 3x cube, right? X cube. So we get 3x squared minus 5. So that really means that we have now 3 zeros, right? So from here we can write down the zeros. So that gives us zeros. So zeros at x equals to 0 with multiplicity of 3 and x equals 2 plus minus square root of 5 over 3, right? So these are the 2 zeros. So we have a 0 here which is at origin, multiplicity 3, and then we have 2 zeros, one at somewhere here, somewhere there, correct? So these are linear zeros, correct? So basically in these zeros, the graph is going to cross like this. Here, there will be a point of inflection. The graph will go kind of like this, and this 0 going upward. Do you see that part? It matches with what we had thought about. So this multiplicity gives you the behavior of the function near the zeros. Does it make sense to you? So this is one thing which we get. Now, we also understand, since we say it's a continuous graph, so we can now write here domain and range also. We can say domain is x belongs to real numbers, right? And range is y belongs to real numbers, right? Since it is a continuous function, right, as you can see, domain range is all real numbers. Now that is the basic from the characteristics itself. Now let's find the first derivative. So the first derivative of the function is 15x to the power of 4 minus 15x squared. Now here we could factor 15x squared, so we get x squared minus 1, which gives you 15x squared, x plus 1 times x minus 1. So we get now the critical points, right? So we have critical points. We can say critical number for time being. So the critical numbers are x equal to 0, x equal to minus 1, and x equals to plus 1. So these are the three critical numbers, and at these numbers we need to analyze for local maximum or local minimum. Clear? So we could do it very easily by sketching these critical numbers here. So we are saying that we have order 2 here at 0, right? So it is the turning point, correct? Is like a quartic function. We have one here on this side, one here on the other side. So basically it has to move positive. So it is kind of like this. So this is the graph of the derivative. Is that clear to you? Now, from the graph itself, you can say about the local maximum and minimum. So let me use this space. Now, as you can see at minus 1, this is minus 1, the derivative changes from positive to negative, right? So positive means increasing, right? So it is like the graph is increasing and then decreasing, correct? So at x equals to minus 1, we have local maximum. Clear? Since the graph changes from increasing to decreasing. Is that clear to you? At x equals to 0, there is nothing happening here. The graph is actually negative. Do you see that? So it is decreasing, and then after that also it is decreasing. So probably a point of inflection, but neither. So local maximum. Let's find the coordinates of this local maximum by putting the value of f equals to minus 1. So if I substitute minus 1 here, I get minus 3 minus 5 times minus 1, which gives us positive 2, right? So the value of local maximum is what? Local maximum is at minus 1, 2. Clear? Now we don't have any maximum minimum here, but at point which is x equals to 1, we again see that it changes from negative to positive. So at this point, it is going positive, right? So from negative to positive means local minimum. So at x equals to 1, we have local minimum. Clear? So let's find this value also at 1. So at f equals to 1, substituting 1 here, we get 3 minus 5, which is minus 2. So we have local minimum at 1 minus 2. Clear? So on this graph, we just found that we have a turning point here, which is a local maximum. We have a turning point here, which is local minimum. And the coordinates for this point is minus 1, 2. The coordinates of the other point is 1 minus 2. Is that clear to you? Okay. Now, from the given scenario, you could also see that's an odd function. And from this kind of a sketch also, we saw that this is an odd function. Correct? So let's talk about odd function and even function. That's another characteristic. So if I calculate what is f of minus x, what do I get here? I get 3 times minus x to the power of 5 minus 5 times minus x to the power of 3. So these are negative values, right? So we get negative 3x to the power of 5, positive 5x cubed, right? So which is negative of f of x. Do you see that? So therefore, the given function f of x has odd symmetry. Is that clear to you? So this is symmetric about origin. So that means it is symmetric about origin. That's why we got that matching pair. Do you see that part? So this is also a very important characteristics which you could write down. Now second, from the same first derivative analysis, we have seen about where the first derivative is positive, where it is negative. Correct? So we know that the function is increasing. So let's write down the interval for increasing and decreasing. So I'll just squeeze in here in a different ink, increasing interval. So the function is basically increasing in the interval when the derivative is positive. So that means it is increasing from when x is less than minus 1, it is increasing, correct? And then it is positive when it is greater than 1. So when x is greater than 1, it is increasing. About decreasing interval, the function is decreasing in between, right? So from minus 1 to plus 1, right? Being 0 at this point of inflection, correct? So at times we kind of write this, it's kind of 0, but it is decreasing all the way. So we can say when x is greater than minus 1 and when it is less than 1, it is decreasing. So these are increasing and decreasing intervals which are also very important, correct? So we got the critical numbers and we got local maximum, minimum and increasing, decreasing interval from the first derivative. Is that clear? Right? So now we are going to write down the second derivative and analyze the second derivative on a separate sheet. So let me show you this part clearly here. What we had done here was that we sketched the first derivative. First derivative is a quadratic function as shown here. It is 0 at minus 1, 0 and 1. It is positive on the left side. That means the function is increasing on left side of minus 1. It is negative in between 1 and minus 1. So function is decreasing in this interval. And after 1, it is positive. That means the function is increasing. So from here, we get local maximum at minus 1, local minimum at 1, increasing and decreasing intervals also from this graph. Is that clear to you? Now, let us analyze the second derivative where we are going to discuss the concavity. Correct? So, let's find the second derivative now for the function. We are given that the function is 3x to the power of 5 minus 5x cubed. The first derivative we just found was 15x to the power of 4 minus 15x squared. Let's find the second derivative now. So 4 times 6, 15 means 60, x cubed, 30 minus, okay, 30x, right? Now you could factor 30x from here. So you get 2x squared minus 1. Okay. So that is your second derivative. So we have second derivative is 0 for the values x equals to 0 and x equals to plus minus 1 over 2 square root. Is that clear? So we got 3 zeros for the second derivative. Let's try to analyze this second derivative here. So we'll analyze the second derivative here. So we have 3 zeros, one at 0, the other two at plus and minus half, square root, right? So minus 1 over square root 2, then we have plus 1 over square root 2. These are the two. Okay. Now I could write this second derivative as, okay, so what we'll do here is we'll write these three factors. So these three factors are 30x, and then we have, we could factor this actually and write this as square root 2x plus 1, and we could also write this as square root 2x minus 1, right? So those are the other two factors. So in this, let's take a test point. Let's say this is minus 1 here, and let's say this is a small point which is minus 0.1. So we'll take 0.1 and 1 here, correct? So these are the critical points to check. So at these critical points, whenever it is negative, 30x will be negative, this is negative, these two will be positive, correct? Now, when we have this plus thing here, in that case, putting minus 1 will give you positive here, and here also it is going to be positive, right? So no, this factor is going to be negative. When I write minus 1 here, then square root 2 is more than 1, 1.4. This will be negative, sorry. However, this will be positive, this will be positive, that will also be positive. Now, when I substitute minus 1 here, this will be negative, this is negative, this is negative, both are negative. And when I wrote 0.1, that will be negative. And when I write 1 here, in that case, this is going to be, square root 2 times 1 will be positive. So that is how we are going to get the concavity. So as you can see that the concavity for the function is, in this case, negative. So in this interval, it is negative, right? So when it's on the left side of this is negative. On the right side of this, negative and negative makes it positive. And then again, you have negative and then you have positive, right? So that is the concavity. So that really means that the function will be concave down for negative, concave up, concave down, concave up when it is positive. So the concavity changes at plus and minus square root 2, and it also changes at 0. So we have 3 points of inflection. So we can write down here that we have points of inflections at x equals to 0 and plus minus 1 over square root 2. Is that clear? Correct? So these are the 3 points of inflection. So, and we also understand that the concavity of the function is kind of like this. Now, based on this, let us now sketch our function. Okay? Right. So, let me just draw a rough sketch here. So from the previous page, the important things which we got are the intercepts, which are at 0, x-intercepts minus 1 and plus 1, right? We got point of inflections now, and we got maximum and minimum value. So let me just make a rough sketch from all this, what we have got. So I'll just fill in the values here. So we have these 2 points, which are rather 3 points, which are a point of inflection, and this happens at minus 1 over square root 2. That is at 0, and this one is at plus 1 over square root 2. I'm not really calculating the value, which you should be calculating, but I'm sketching the curve with these additional values. Intercepts at minus 1 and plus 1. Clear? So I'll make a bigger view here. So the graph will look like this. So we have a turning point here at minus 1 and 2. Is that okay? Now this graph is kind of like this, where this 0 is at minus 1. 0 we calculated was at, let's see, what was the 0 values. So when we factored, we had 0 at 0 and plus minus square root 5 over 3, right? So square root 5 over 3. This value is negative, square root 5 over 3. Okay. Now we have a point of inflection here. Okay. So the curve and a point of inflection at 1 over square root 2 also, right? So this graph goes like this, and at this point, which is minus 1 over square root 2, we have point of inflection. So it turns kind of like this. Do you see that part? And then we get this point of inflection at 0. Is that clear? Similarly, we are going to have a point of inflection here with a minimum value of minus 2, right? So at 1, we are expecting a minimum value of minus 2. It is odd symmetry, so is this going to turn here with this kind of function and then go up, right? Where this point here will be square root of 5 over 3. Is that clear? Now, clearly, somewhere here, which is at 1 over square root of 2, we get a point of inflection. So let me put a star at the point of inflection, which are these points. Is that clear to you? So that is the graph for the given function. So I hope these steps are absolutely clear. So what we did was that we analyzed the function. We found this a polynomial, continuous function, domain range all real numbers, found the zeros, then analyzed the first derivative. To analyze the critical numbers, we found local minimum and maximum at plus minus 1. Then we analyzed the second derivative to find point of inflections, 3 of them, at plus minus 1 over square root 2 and 0. And then we sketched it based on the information. So that is how we are going to answer this test paper. I hope you find it interesting and useful. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.